Hi, AP Calculus students. Welcome to section 3.7 on optimization. Optimization, right? Optimum points are maximums and minimums. So we're just going to be finding maximums and minimums, which you know how to do, right? But applied to real world situations, right? What could be better? Why just find max and mins? Why do they mean anything? Sure, they do. So, because we are always trying to maximize our output and minimize our cost and time, we are going to have real world functions where we're finding max and mins. So here's a picture, right? And of course, here's a maximum and a minimum. If this were a volume function, right, which would be cubic, so that makes sense. I drew a cubic graph for a box. So it's a volume for a box given set materials, like you have so much material. What would the maximum be, right? It would be the maximum volume given the materials that we have. And that's what we would want to know because our materials cost money. So what's the maximum use we can get from those materials? What if this were a time function that were in a cubic shape? Given a job to be completed, I forgot an N there. Given a job to be completed, what would the minimum be? Right? So that would be the minimum time it takes to do the job, which would save us time and money, which is a point that we really might want to know. Okay. Here are our steps to finding solutions to optimization problems. Okay, so I might actually just scooch this in a little bit because I think the writing's just a little small. There we go. It makes me a little bigger though, doesn't it? Okay, there we go. Finding solutions to optimization problems. This is similar to our steps for related rates. We are first going to identify all the quantities we've been given and to be determined and draw a picture if possible. We're going to write a primary equation, right? What is a picture that we have? What are we trying to maximize and minimize? So we're going to write a primary equation to maximize and minimize. We'll mark it that we're trying to maximize or minimize, remind ourselves of what we're looking for, and talk about a feasible domain, right? If we're trying to find a time at a minimum to get a job done, we're obviously going to not have negative values. If we're trying to find a volume, it's obviously going to have to be greater than 0, right? C, we will use secondary information if needed to substitute in the primary equation if the function has more than one independent variable. So some equations we write, good to go. Primary equation, one independent variable, let's go ahead, take the derivative, find max and mins, right? But if it turns out we have more than one variable, then we'll do substitution. We did that in related rates. Then we will take the derivative of our primary equation and use our first derivative chart to find the max and mins. And then we'll just check our solution with logic. And did we actually answer the right question, right? If we find the side length of a box that we're trying to find the maximum volume, if they ask us what that volume is, we have to answer that question too, not just what are the dimensions of the box. So we have to make sure we're answering the right questions, okay? So I'm just gonna bring you over here, right? So what I'm gonna be doing is problem 23C and number 16 for 3.7A for that assignment. And I'm sure I'll do some examples for 3.7B also, but let's take a look here, just trying to make this a little bit bigger for you in my workspace here. I was trying to fit everything on one board. There we go. Okay, so they are asking us to find the maximum volume of a box with a square base. So notice I made the front and the back square, and a surface area of 150 inches squared, right? Surface area is material. So given a set amount of material, what's the maximum volume we can make when we need a square base? And this makes sense. So what I'm going to do is I'm going to mark the square base. I'm going to call this X, right? And X, since it's a square. And the distance between the bases, I can call anything I want, but I'll call it H. right? So the first thing we did, we identified all the quantities to be determined, and we drew a picture. Now we're going to write a primary equation. They are asking us to maximize the volume, and so we need to write a volume equation. So my volume equation for this box is x squared times h. Okay, and I'm just going to write here that I'm trying to maximize that volume. That's what I'm trying to do, okay, to remind myself. Now, secondary information, I need to substitute into the primary equation if there's more than one variable. Okay, so notice that they did give me secondary information, that the surface area is 150 inches squared, and I'm going to use that information to substitute in for h so that I only am working with x's, okay? This is going to take a little bit to get that h, and then we'll rewrite our volume equation and start from there. So you may see some erasing, right? I'm going to need some room, so write with me so that you get what I end up erasing. So here's the surface area. The surface area is 150 square inches. And what is the surface area? Well, the surface area are these 6 faces added up, right? So notice I have an x squared surface area in the front and the back. So I have 2x squared. And then plus I have 4 sides that make up the surface area, 4 rectangles, and those are x times h. Okay, so what I'm going to do is work to get the h